All right, let's say we have a problem like this. X to the n minus 1 equals 0. All right, we know by the fundamental theorem of algebra that that better have n roots. Okay, so let's say that I have x to the n minus 1 where n is 4. Okay, like that. We're going to try to solve that problem. So anytime I'm solving these problems, let's keep it general for a second. So if I have x to the n equal to 1, that's the problem I'm trying to solve. Now, I know that one of the roots is obviously x equals 1, right? So I can say that x equals 1 to the n. Now the thing about that, though, is there has to be more answers, right? I don't just get 1 n times. Now, the thing I need to tell myself is that 1 is equal to e to the j 0 degrees. How do I know that? Because I can expand that as cosine 0 plus j sine 0. This guy would be equal to 0. This guy would be equal to 1, right? I also know that a vector, so if I sketch that vector, so here's the real and imaginary axes, that would have basically be a vector with an angle of 1, or sorry, a magnitude of 1 and an angle of 0. Okay, so I know that if I also had a vector with a magnitude of 1 and an angle of 360 degrees, that would be the same thing. Would also be the same as 2 times 360 degrees, or 3 times 360 degrees, like so. All right. Now this is described in the book, all right, but it's a little bit easier to maybe see it if I take it this way, right? I know that the angle 0 and the angle 360 are the same. The angle 360 and the angle 720 are the same. Okay. So what I can do is I can go back and I can say, well, x to the n is equal to e to the j 360 times k, right? I'll say 360 degrees, all right? I could also do that as 2 pi radians if I wanted to, all right? And in this case, I do this for k equal to 0, 1, all the way up to n minus 1. That will give me n roots, okay? So in my example, I said let's do x fourth equals minus 1. The way that I would approach this is I'd say, well, I know I need answers for k equal to 0, 1, 2, and 3. That'll give me 4 roots. So x to the fourth equals e to the j 0 degrees. Okay, e to the j 0. It's also equal to e to the j 360 degrees. It's also equal to e to the j 2 times 360 degrees. And it's also equal to e to the j 3 times 360 degrees. Like that. Okay? So I can solve this guy by saying x has to be equal to e to the j 0 degrees, e to the j 360 divided by 4, e to the j 2 times 360 divided by 4, and e to the j 3 times 360 divided by 4. Now you should be able to see real quick, 360 divided by 4 is 90, sorry. So 360 divided by 4 is 90. So I can say that my answer here is e to the j 0, e to the j 90 degrees, e to the j 180 degrees, and e to the j 270 degrees. So if I were to plot those vectors, so here's real Here's imaginary. E to the j0 is there. E to the j90 is there. E to the j180 is there. And e to the j270 is here. All right. Now in this case, I can say that each of these, okay, it's a very poor drawing here, but basically each of these is the radius of a circle I call the unit circle. Now to better visualize that, because clearly that is a terrible drawing, to better visualize that, I wrote a little piece of Matlab code here. All right. So in this case, the Matlab code that I wrote, what I've done is I have tried to solve that problem. So let's look at these two things kind of side by side here. All right, so basically what I've done is I have said, let me define a vector k going from 0 to 3, and let me define all the angles. So in this case I said I have a vector angles, which is equal to 360 times k. Okay, and I added a 0 to that. We'll talk about why I did that here in a little bit. And then I defined x as the exponential j times, now notice what I did. I took angles and multiplied by pi over 180. Why did I do that? Well, the reason I multiply by pi over 180 is because the exponential function is in radians, right? So if I have an angle in radians, so if I have an angle with units of radians, or actually in this case it's degrees, an angle in degrees, and I multiply by, in this case, pi radians over 180 degrees. That's basically a unit conversion, right, to go from degrees to radians. Now I know your calculator can do that. I know Matlab has a function for that. This is just a unit conversion, right? So you should be able to kind of think about how this is set up. All right, so what I'm doing is I'm saying that my answer is exponential j of the angle, the set of angles I have, all right, in radians, times the 1/4 power. Okay. Now that vector, what I then do is I plot that using this compass function. All right, that's shown in that script 4.1 in the textbook. All right, so if I want to run that code, let's do that. I can highlight that code right there, and I can then right-click and go to Evaluate Current Selection. All right, now when I do that, here's that compass. So basically what I can see is it's showing me here, each of these lines here has a different radius. So this line has a radius of 0.2, this one 0.4, 0.6, 0.8, and 1. Okay, and then these marks here are showing me angles. This is 0 degrees, 30, 60, 90, so on and so forth. Okay. The outer edge here is the unit circle. There's a circle with a radius of 1. Now notice what is plotted here. What's plotted is these 4 roots of unity that we wrote over here that I'm highlighting. Right? So I see something with an angle of 0, one with an angle of 90 degrees, one with an angle of 180 degrees, one with an angle of 270 degrees. What I notice is that these vectors, all right, are all an equal angle apart from each other, and they span the full circle. In other words, in this case, I have 4 of them, and they're 90 degrees apart. If I had 3 of them, they'd be 120 degrees apart. If I had 2 of them, they'd be 180 degrees apart. Right? So the distance between them is always going to be 360 degrees divided by n, no matter what. Okay? Now let's look at a similar problem that's maybe a little bit more difficult. All right? So a similar problem that I might look at would be this guy. let's say I had x to the n minus r equals 0. So again, we know that by the fundamental theorem of algebra, there better be n roots. In this case, r is in general some complex number. All right, so I know then that x to the n is equal to r. Now r is some complex number, so I can say that r is got a magnitude r and an angle e to the j angle r. Okay, so it's a complex number. It looks like that. Okay, so in this case, what do I know? I know that x to the n is equal to r e to the j angle r. I also know that if I added 360 degrees to that angle, I would have exactly the same vector. So in other words, this guy is equal to a vector with a magnitude r and e to the j angle r plus 360 degrees, like that. It would also be equal to a vector with a magnitude of r and e to the j angle r plus 2 times 360 degrees. Okay? And I could keep doing that until I had basically reached the number I need to get all my nth roots. Okay? All right, so if I want to figure out what my solutions are, basically what I have is that x, I guess I'll call it x0, would be equal to r to the 1 over n times e to the j angle r divided by n. Then I could say x1 is equal to magnitude of r to the 1 over n power. And I say this guy has an angle of j angle r plus 360 degrees divided by n. x2 is the magnitude of r to the 1 over n e to the j angle r plus 2 times 360 degrees divided by n. And this would continue all the way down to x n minus 1. The magnitude is still r to the 1 over n power times e to the j angle r plus n minus 1 times 360 degrees divided by n. Okay, so let's look at that in sort of an example problem. All right, in this case, I'm going to say that I have x to the n power equals, well, it's specifically not x to the n power. We're going to say x to the third equals minus 4 minus 2j, like that. So essentially what I'm solving for here is, so I'm solving for, in this case, minus 4 minus 2j to the 1/3 power. Okay? All right, so here's how I'm going to approach this problem. First of all, to be able to solve it, I need to get this vector here. So I need to get this vector r. I need to get r into polar or complex exponential form. So the way I do that is I look at this guy. Okay, let's draw this complex plane. So here's real, here's imaginary. I know that this minus 4 minus 2j must be over here in the third quadrant. Now again, I'm always careful with that because I know when I'm in the third quadrant, I have to be careful with the arctan function. And I have to add 180 degrees to whatever angle it is that I get. Okay, so in this case, if I want to figure out the magnitude of r, the magnitude of r is simply the square root of 4 squared plus 2 squared. Okay? And the angle of r would be equal to arctan of imaginary over real, so minus 2 over minus 4. Notice that just becomes 2 over 4. All right, that's particularly important because, in other words, what I see is I get the same answer down in the third quadrant that I would get in the first quadrant. So I got to be careful here. I know this guy's in the third quadrant, so I have to add 180 degrees to whatever it is that I get. So if I do that arctangent, what I end up getting is, in this case, 26.57 degrees. And I add that to 180 to get effectively 206.57 degrees. So I always do kind of a sanity check. I know that this line over here has to be 180, this line has to be at 270. So 206 seems about right given the way I've drawn that. Okay. All right. So let's keep going. All right. Now, what do I have to do? Well, I basically have to figure out x0, x1, and x2. Okay. In each case, I take the magnitude of r and raise it to the 1/3 power. Now in this case, I take e to the j angle r and raise it to the 1/3 power. For this guy, I take e to the j angle r plus 360 degrees divided by 3. And for this guy, I take e to the j angle r plus 2 times 360 degrees and divide it by 3. All right? And I go about calculating that way. Now, again, that's probably easiest to do in Matlab. Okay? So here's how I approach that in Matlab. So I wrote a piece of code. So I have r equals minus 4 minus 2j. And then I have my angle r that I compute. So notice I take the atan of imaginary over real. Right? Now I convert it, by default, arctan comes out in Matlab in radians. I convert it to degrees using that unit conversion, and then I add the 180 to it. Then I get the magnitude of it. Now here's what I do to get the result. Right? Basically what I do is I say I create a vector k, which goes up in increments of 1 from 0 to 2. Okay, so there's basically going to be 3 entries in that vector. And then I come up with the set of angles that I need. So let's look for ourselves. Let me set this guy over here. All right. So the angles I created, so I took the angle of r and I add to it k times 360 degrees. So when k equals 0, that angle would simply be angle of r. When k equals 1, in this case, I would get the angle of r plus 360 degrees. And when k equals 2 here, I would get the angle of r plus 2 times 360 degrees. All right, now to get those cube roots of this thing, notice what I did. I created the magnitude, or the vector a, and I said I've got the magnitude of r to the 1/3 power times exponential j times, and now I converted my angles back to radians, and then I multiplied by 1/3. Okay, so let's see what that looks like. Highlight that guy again, right click, and I go to evaluate current selection, and that just evaluates that code, and I get this guy. Okay, now looking at this thing here real quick, right? Notice, what do I have? If I look at these 3 vectors, the really important thing that jumps out to me about these 3 vectors is they look like they're 120 degrees apart, right? What did we say? We said that for our answers, it better always be the case that the vectors have a spacing between them of 360 divided by n degrees. So in this case, that's 360 divided by 3, or 120 degrees. And it looks like they do. All right, now I'm going to try to do a check on that. The way I'm going to try to do a check on that, all right, I'm going to take this angles vector right here. I'm going to copy that and paste it into Matlab. Okay. I know that the angles of the result should be separated by that much. So if I took angles divided by 3, those are the angles of the 3 results. So let me do this. I'm going to type diff. I'm going to use this function diff. Let me type help diff. All right, diff is something I know. So diff x for a vector x takes the difference between 2 adjacent entries. So I'm going to do diff of, so if I just did diff of angles, right? So angles was the vector I created over here, where what I did was I was adding 360 degrees each time. The difference between them better be 360 degrees, and it is. This says that the difference between entry 1 and entry 2 is 360 degrees, and entry 2 and entry 3 is 360 degrees. So if I did diff of angles over 3, which is the angles of the result, I see there's 120 degrees between them. All right. So really important result is you can always kind of check your answers for these types of problems by noting that the answers I get better be 360 divided by n degrees apart. Now I wanted to point out here, I did this second problem again, right, using some of Matlab's kind of special sauce. So what I did was I said the magnitude has to be equal to abs, or the absolute value of r. To see that, I type help abs. Okay, absolute value. Abs x is the absolute value of the elements of x. When x is complex, abs of x is the complex modulus or magnitude of the elements of x. Okay, so this guy is the magnitude of that vector. The other thing I could do, instead of having to do this atan business and thinking about how to deal with it, I can just ask Matlab for the angle of that complex number. And then I converted it to degrees for myself. And then did everything here for A2 that I did previously. And so I should get the same result, except with fewer lines of code. So notice what I'm doing here. I'm highlighting just a particular section of code, and I'm right-clicking, and I'm saying I want to evaluate just that section of code, and I get exactly what I had before. All right, so hopefully that helps to understand some of these issues about nth roots of a complex number.